Okay, off we go. So here's what we were talking about last time. We were talking about the implicit function theorem. So let me remind you what the big idea is of the implicit function theorem. So you start off with a level set, and of course a level set could be some curve like this, right? That could be a level set of some function. And the question, well, let me start off with what the question isn't. The question is not, is this the graph of some function? Because that's obvious. It's clearly a failure of the vertical line test. Obviously not a graph. Pointless. Here's what the question is. We refine the question by saying locally. What we mean by locally is, suppose I restricted my attention to just a part of the curve. So I'm no longer going to look at the entire curve, right? I'm going to look just at the part that's nearby the point in question. And what do I mean by nearby? Make that as small as you want. Make this little yellow ball here as small as you want it to be, small as it needs to be. So that then is the question, is this the graph of some function? And you see, absolutely, fine, no problem, passes the vertical line test. So why would we be interested in such a thing? Right? Why would we be interested in whether something is locally a graph? Well, because derivatives are a convenient tool. We like to be able to take derivatives of things. And you can't take derivatives of stuff that isn't a function. Right? So if we're looking at a picture, and if I want to be able to say, hey, the derivative is the slope of the graph of whatever function is this is the graph of. Well, then I need to know that it actually is before I can go around talking about the derivative, right? So the obvious failure is at this point up here, where you can see no matter how little of the curve I look at that point, right? No matter how local I want to get here, it doesn't matter how much you restrict your attention. Just some nearby little region, it's going to fail the vertical line test, no matter how little you're talking about. So I cannot even ask the question of what is the derivative here, because this isn't a graph of some function. We take derivatives of functions. Right? Does everybody see the point? Right? So not only can I not compute dy dx, I can't even ask what is dy dx. I can't even talk about dy dx. It's not a thing. Okay, all right, so that was the big point of why we start this whole process. And then here again is sort of the quick answer to the question. And roughly speaking, the problem, what I'm going to call the problem here is that the curve wraps under itself, and you can see pretty easily that's in some sense why we fail the vertical line test, right? And okay, well if it's wrapping under itself, then it has a vertical tangent line at that point. Notice I did not say that the derivative is infinity or something like that, because I have not yet established that I can even talk about the derivative. And in fact, in this case, I cannot talk. There is no derivative to talk about, certainly not in terms of slopes, because that's not the graph of a function. Right? So you've got to be careful with the wording. The point here has got nothing to do with any sort of a derivative. The point is that there's a tangent line and it's vertical. And then we remember, of course, that gradients have this feature that gradients are perpendicular to the tangent line, because it's perpendicular to the level set. And that means it's horizontal. Horizontal means that the vertical component is 0, right? And this is our basic argument, which I'm going to summarize by highlighting that if you have a problem, then the y partial is 0, right? And then we point out that, okay, well, yeah, this I can turn this upside down and backwards by using the contrapositive, right? Very important construction, the contrapositive. The contrapositive then says, well, if that partial is not 0, then that must mean that there couldn't possibly be a problem, because if it were, then it would be, so therefore, no problem. Okay, so this is our first example, sort of, appearance of the implicit function theorem. And I'm going to summarize it by saying whichever variable you want to view as being a function. I wanted to switch the color there. Sorry. Whichever variable you want to view, whether it is or isn't a function, that's the variable that you take the partial with respect to. Notice that pattern. Now we're going to, again, I think we've already talked about, we did this on Friday, right? Oh, yes, question.
So on the previous slide, the two bottom points, and would you explain the bottom?
Yeah, you can't take the derivative of something that's not a function.
Oh, sorry, like the
Sorry.
A little bit.
Up.
Sorry. Like the leftmost point, how can that not be viewed as a local function?
Yeah, so because keep in mind locally, right? Locally means I only care about only what's inside of the yellow. That's all I care about. And inside of the yellow, that's the only part of the curve that's inside of the yellow. When you're talking locally, I don't care about any of that or any of that or any of that. It's just absolutely irrelevant to the question, the local question, right? So locally, all I have is a little green piece of curve, and everything's fine. Yeah. Okay. So, so let's take I think this is a reminder of the three-dimensional version of the question, because I think we did talk about this. I think this may have been the very last thing that we did, right? It's surprisingly similar, frankly. Some points I can do this, right? There are some points, for example, let's say a point there, and locally, if I restrict my attention just nearby there, and if I look just at this, I wanted the pencil. I want to look just at that part of the surface. Yeah, it's fine, right? This is the graph of some function. I can view z as a function of x and y here because you could imagine a little vertical line test happening. It only hits the green part of the surface, again, locally, being all that we care about. Every vertical line hits that green part of the surface once. No problem, no issue, all good. Likewise, most of the other points, but then, of course, the problem. The problem happens there. The problem being that is where not the curve, but the surface is wrapping under itself. That's going to be that's why this isn't going to be possible to make it work. It's because at that exact very point is where the surface actually successfully, finally, at its first instance, kind of wraps under itself. So the fact that it wraps under is the problem. It wraps under when you have a vertical tangent plane. And a vertical tangent plane means that you have a horizontal gradient. Keep in mind, when we say horizontal gradient, we mean gradient of f being the function that this is the level set of. Gradients are always perpendicular level sets. And so again, we have ourselves a result that we can kind of turn around backwards. If we had a problem, then the vertical component would have to be 0, namely this z partial would have to be 0. So turning that around backwards, if this does not happen, then that does not happen. If the z partial is not 0, no problem. Okay. All right, so shockingly similar motivation. I don't want to, this is not a proof. There's all sorts of rigor crimes that I'm committing here. Appropriate to the course. But again, I want you to notice in terms of pattern, the variable that you want to view as being a function, that's the variable you take the partial with respect to. What do you take the partial of? You take the partial of the function whose level set describes the surface that you're talking about. Okay, remember, of course, a lot of detailed devils about the difference between a function whose level set is a given surface, on the other hand, a function whose graph is the surface versus a function that parameterizes a surface, right? All these different geometric algebraic connections. You got to pick the right one. Here, the key concept is level set. Okay. Okay, so now let me just kind of summarize. I claim that this generalizes, and again, we don't want to get all ugly with the rigor here. If you're looking at a level set, and you want to ask locally, can I view one of the variables, right? This variable xi, that's one of these variables. Can I view one of these variables as being a function of the others so I can talk about its derivatives, right? Its partial derivatives. Then the answer is whichever variable you want to view as being a function, that's what you take the partial with respect to. Whichever function whose level set describes your surface, that's what you take the partial of. And if you get non-zero, then yes, you can view that variable as a function of the others. Yes, you can talk about its derivatives, its partial derivatives, etc. Okay, so generalizes exactly how you would kind of, I'm going to say exactly how you kind of hope. Okay, example. So here is a function, an equation. Describes a surface. What does that surface look like? Oh, I have no idea. Right? That's algebraically outside of our experience. Right? So I have no idea what this surface looks like. So I cannot look at the picture and just see visibly, oh yeah, well clearly, we've got a problem here, but all these points over here are fine, right? We have no geometric intuition on this. But if I want to ask, can x be viewed locally as a function of y and z? I want to view x as being a function. Take a partial with respect to x. What do I take a partial of? Well, whatever function whose level set describes your surface, that's what we take the partial of. Right? We're interested in what's happening in the locally near the point 1, 2, 3. So I'm going to plug in the point 1, 2, 3. Not zero, no problem. Everybody okay? It's very plug and chug right into the theorem. Okay. All right. Now the next natural question to come up, and let's just, for pointing purposes, let's think about this example. We've established that yes, indeed, in the neighborhood, in the vicinity of, locally near this point 1, 2, 3 on the surface, I can view x locally as a function of y and z. Cool. I can treat x as a function near that point. And if I can treat it as a function, then I can take partial derivatives of it, right? After all, x is now, at least locally, a function of two variables. Functions of multiple variables, you can talk about holding one constant, taking the partial with respect to the other, and what do you get? So, natural question. Now that we've established that x is a function, how do I take its partial derivatives? So, for example, I might talk about the partial of x with respect to y. Or I might talk about the partial of x with respect to z. All good. Bad news, good news. Bad news is this is what I would call a thorough take on how to answer that question, and it's a lot to absorb. It's a lot going on. And here's the good news. There is a much more streamlined version of this diagram, and I'm going to show you the streamlined version of the diagram. I don't really want to walk through all of this stuff. You're very welcome and encouraged to read it, of course, but here's the streamlined version. Now, the first thing you're going to notice is that in my streamlined version, I have a diagram that does not follow my own rules. And I want to recognize that right off the bat. Right? So what gives me the big head to think that it's okay for me to make a diagram that doesn't satisfy my own rules? Well, I claim that this is really just a kind of a compactified, sort of streamlined version of this. And you'll notice this does satisfy my rules. I have a composition here, intermediate variables there, second function right here. This This is all good. This is a regular old composition of multivariable functions. And I claim that really this is saying the same thing, just in a more sort of compact way. So the big idea, let me just walk you through it. Big idea is we've got f, and that's a function of all these variables. That's what we're given. And keep in mind, it's constant. It's not allowed to change. And then we've made the observation that even though all of those variables are input variables, we've now established that xi, or we have rules for how to establish that xi is a function of all the other variables. Yeah, that didn't. That didn't work out the way I wanted it to. Let me try that again. No, I missed it again. Okay, third time's the charm. There we go. Xi is a function of the others. And again, I'm breaking my rules, and they're in the same sort of column, and you're not really supposed to do that. But again, this is harmless in this case, as it turns out, because again, we're really just doing this. Okay, so let's just, strategically now, let's just think, all right, well, look, if this function here is not changing, its derivative is 0, right? It's a constant. Constant means derivative is 0, not changing at all. And let's just keep track now then. How do I get that 0 if xj changes? What are all the different ways that changes in xj could propagate to cause changes in f? And roughly speaking, there's two ways it can happen. On the one hand, changes in xj. Well, xj is literally one of the input variables for f. So when you change xj, it will directly contribute to how much f is changing. But wait a second, there's also this other path, like so, by way of xi. Xj causes changes in xi, and xi causes changes in f. And those are the only two things that can really happen, but because of course we're talking about partial with respect to xj. Partial means all the other inputs to xi are held constant. So all of these other variables have to be constant because we're taking the partial of xi with respect to xj. So that's the only two different paths along which changes can propagate. And again, f is constant. That's why this total has to be 0. And then, wait a second, what are we doing with all this in the first place? The whole reason we wrote any of this down is that we were trying to compute this partial derivative. And so you can just solve for that in the equation. And there you go. Here's your handy-dandy formula for the implicit differentiation of xi with respect to xj. Everybody all right? Now, I want to point out there's something very, I'm going to say, what's the word here? Unexpected, I think is a fair statement. And that's this minus sign. I'm going to call it unexpected because here's the tempting, nonsensical, but still tempting thing you're going to want to do. You're going to want to say, ooh, hey, partial f, let me just cancel those. And let's see, now wait a second. Now I have, this is in the denominator of my denominator. Shouldn't that go up to the numerator? Oh, yeah, sweet. That's where it is. And let's see, this is in the denominator of my numerator. Well, that's the denominator. Oh my gosh, this the sort of the playing with fractions argument here would suggest that this derivative is literally just this ratio. No minus sign. So a lot of people look at this and say, well, that's weird that there's a minus sign. That seems kind of wrong somehow, right? It's not. This little argument about cancellations, remember we talked about this before, especially when you're dealing with the chain rule, when there's multiple variables, the intermediate space has multiple variables, you just straight up flat cannot treat these as fractions. They are not fractions. This partial f and that partial f, they're not the same thing. There is no cancellation to be done. The notation's unfortunate. The notation makes it look like they're the same things. They're not, right? So it's a completely nonsensical argument to suggest that there's something wrong with there being a minus sign here. Is everybody on board with that? Yes?
This is like a point from before, but are we just not taking the partial, like, dx1, dx1?
Correct, because, so keep in mind that xi is a function of all of these other variables, right? And when we say I want to take the partial with respect to xj, what that means is all these other variables have to be held constant. That's how partial derivatives work, right?
But like, if you also do like, or I'm assuming that you're going to need to do like added on like a plus df divided by dx1, dxj.
Yeah, correct, because the partial of x1 with respect to xj is by definition 0. So yeah, so that's right. I mean, if you want to say that there are terms there, yeah, I guess you can, but they're 0, so we just don't bother writing them down. Yep. Right. Okay. All right. Another point of view for your consideration. Maybe this will appeal, right? Suppose you wanted to convince yourself that this ought to be a plus, which it's not. Don't write this down, right? But suppose you wanted to suppose you wanted to argue that that should be a plus. Well, that'd be like arguing that this should be a minus. And why would that make sense? We're trying to compute the grand total of how much f is changing. And when you want to compute a total, you add contributions. This being a plus is exactly why that needs to be a minus. So another way to think about it. Here, last comment on this. If this were a minus, we would have a difference equaling 0. That would somehow suggest that this would be equal to that. Well, why on earth should that be the case? How would they be equal? There's no argument there. Right? So it's just nonsense. So anyway, here's why I make a big deal out of this. This minus sign is the only thing in this equation that distinguishes the student who wrote it down from someone who has absolutely all the wrong ideas about the chain. Right? That minus sign is the only way that you distinguish yourself from someone who has no idea what's actually going on. Right? And that's a big that's a distinction that y'all should definitely want to make, right? You want to definitely remove all possible doubt that you might actually believe that these df's, partial f's, cancel. Oh, gross, right? You don't want to be associated with that. So make extra sure that you remember this minus sign. It's enormous. You got to keep in mind when we're grading exam papers, right? We don't know what you know. All we know is what's written on the page, right? And if you forget this minus sign, oh golly, now I've got to struggle and try to figure. Okay, is that an inadvertent mistake, or is that just literally not understanding important ideas? And that's not a question you want your grader struggling with. Okay, so again, I have to make a big deal out. The bigger deal that I make out of this, the fewer students forget it. Right? So very important. Don't make that mistake. All right, so let's do the calculation here. Y'all will recall we looked at this example previously. We were interested in this surface. We were looking near the point 1, 2, 3. We've already established that x is locally a function of y and z. We did that in the previous example. X being as it is a function of y and z, I can talk about its partials. And so let's ask the question now, how would I compute that partial? Now I'm going to make a confession as to how I remember the formula, how I sort of put things together at this point. Very first thing I encourage y'all to do is to write down the minus sign. Get that on the page. Right? Don't think about other stuff and variables and what's the f and level set. No, get that minus sign on the page. Right? Then once you've got the minus sign on the page, then you come back over to here and you're like, okay, we got the minus sign on the page, and that's that whole thing. But except for that minus sign, this business about cancellation is actually, it's a pretty good little memory tool. Nonsense though it is. Right? But again, we've corrected for the minus sign. That's there. That's in the bank. The way you can make sense out of how to write this down is literally to kind of remember, the whole point is that the partial f's cancel and the denominator of the denominator is the numerator and all that stuff. It's a fantastic little memory tool. And it's a handy memory tool as well because notice the way I set up the variables here, the input variables were x1 through xn. Over here, not at all. Here, my input variables are x, y, z. In some other example that y'all will see in your experience, whatever y'all going to be doing, they'll be called P, K, and L or something, right? So they're always going to be called different things. So please do not memorize this rule character for character. Right? It won't fit when you try to apply it. So I like to remember it in this faux cancellation sense. So again, here's the faux cancellation. And then let's see here. I want the partial of x, so that must go there. And I want the partial with respect to z, so that must go there. Is that cool? Everybody happy? Okay, and now it's plug and chug. Easy partial, easy partial. Punch that out. Don't forget that we're looking near the point 1, 2, 3, so I've got to plug in the point 1, 2, 3, and let's see here. We get as our final result, we get minus 13 halves for this partial there. Everybody happy? Now let me point out one very natural source of confusion on that. I see the following mistake all the time. It's super common. You look at how this question is phrased. Lots of students will look at this and say, oh, it's asking me for a partial with respect to z. So partial with respect to z. Okay, well, so I should take the partial with respect to z, and then they'll take a z partial here. Nope, it's an x partial, not a z partial. So it's confusing, right? There's two different stages of the question. The step one, sort of the first phase of the question, is to address the question of whether x is a function. And it's because of needing to establish that I have to take the partial with respect to x, right? But then subsequently, when I've already established that x is a function, now the remaining partial is a z partial, but that's not what establishes that x is a function in the first place. Okay, so anyway, again, that's a natural little landmine to step on that can really mess you up, so again, be careful about that. Okay, last comment. You'll notice that I wrote this as two examples, right? So the first part of the example was that, and I explicitly point, is x locally a function of y and z? And then the second part, you might say, is what is the value of the partial of x with respect to z? And notice where I assume the conclusion from the previous example, right? So this looks like two different examples, and I want y'all to think of this as two parts in the same example, because here's how it'll typically be phrased, right? Typically on an exam, look back at my old exams if you don't believe me, right? But if you look at any of my old exams, and by the way, again, not because I'm trying to catch y'all on a trick. I'm not trying to fool you, right? But this is how life will come at you, right? In the real world, when you find yourself looking at something like this and needing to compute a derivative, there will be no prompt that says, hey, we better establish that x actually is a function before we start going around taking derivatives of it. It's just not going to be there, right? So the way the question will probably be phrased is like this. It'll say, hey, there's a surface. What's the partial of x with respect to z? That's all it's going to say, right? And you have to remember right? And this is a really important part of the question, that you can't just start writing stuff down like this. I can't just write down partial of x with respect to some. I don't even know if x is a function. Where does it say x is a function of y and z? It's not in the statement of the question. Certainly can't be assumed. And by the way, at some point, it isn't. Right? So what you've got to do when you see a test question like this, step one, do this analysis up here. Step one is to ask that question, establish by this argument that yes, it is. That's the first half of your solution. You have to do it. If you don't do it, then your argument has a massive hole in it. And again, keep in mind, we're not about answers. The answer is not the point. We're about arguments, not answers, and you cannot have a gaping hole in your argument. Right? Just so you know, my past precedent, this is approximate, don't hold me to it, but my past precedent has been that this part of the hypothetical question that I have on the next page, probably about half the points, ballpark, plus or minus, depending on the situation. So, big deal. You've got to establish first that it actually is a function that you can therefore even take derivatives of. And once you've established that it actually is, then you can compute it by way of that second half of the argument. Yep.
So if it isn't a function, is it sufficient to just say?
Oh yeah, if you if you take the appropriate partial and you get 0, for example, so that doesn't actually mean that it's not a function. It means that we cannot conclude that it's a function. And so if that were to happen on a homework exercise, then what you'd want to do is say, I cannot proceed because I cannot establish that this is a function. If it happens on an exam, then you should come up and ask me, because probably what happened is either you've made an arithmetic mistake or I've made a tragic mistake, and I'm going to need to make an announcement to correct the situation. It's going to be one or the other of those two. Yeah. Right. Okay. Alrighty. So, So I've made this point already. Checking whether or not that the variable is a function is an important part of the reasoning, which is, of course, what we're looking for in a valid solution. Okay. Everybody all right? Okay, so moving along. Let's see here. We're going to go over to... I didn't pull up the... Okay, shame on me. Sorry. Give me a second to pull up the second thing here. Okay. Any second now. Chapter 3. Yeah. Okay. All right, so on to Chapter 3, by which I mean the part of Chapter 3 we haven't done already. Remember, we did this little zigzag where I went up and did 3.1 already. That's kind of a convenience, so I can talk about the chain rule the way I want to. So we've done 3.1 off to 3.2. And there's various different parts of this section. Some of this is important setup that we're going to be making a lot of use of over the rest of this course, especially in Chapter 6 and 7. And some of this stuff is what I'm going to call a cool digression that we're basically not going to do much of anything with at all. And so I'm going to spend nice time, comfortable time, I think, on the important first part here, and then the second part I'm going to go through pretty quickly because it's a digression, and ultimately it's a formula you need to be able to plug and chug, so it doesn't need a lot of discussion. Okay, so here's our scenario. Oh, whoa, how did that get so big? Whoopsie. Okay, so suppose we have a parametric curve. So position is a function of time. Right? Time starting at A, ending at B. That traces out a finite parametric curve. And let's consider some little part of the curve. Just a little bitty piece of it, not the whole thing. And let's talk about, what can we say about this little piece of the curve? Well, that piece of the curve, I'm going to say, be traced out in some amount of time dt. and we can talk about what the velocity is of the parametric curve, at least at that starting point. And if you know the velocity and you know that you're going to be going with that velocity, well, approximately, you're going to be going with that velocity for some amount of time dt, the product gives you what I'm going to call dx. So this, gosh, I guess you could call it by various different names. I like to call it the position differential, because that's literally what it is. X tells me the position. Dx, differential, means a linear estimate of a change. So this says linear estimate in the change in our position. And that's what we're doing. Our linear estimate of how much our position changes, well, velocity times time. Right? Is that cool? All right, so position differential, sometimes I call it the vector differential, whatever. Okay, now here's a related question. Let's ask, what is the length of that little piece of curve? Now, how are we going to get our hands on the idea of how long that little piece of curve is? Right, or our linear estimate of the length. And I'm going to point out that a pretty reasonable thing to say is this right here, that the best linear estimate of that length of the piece of curve is that it's the magnitude of the position differential. Dx gives you a displacement. A distance is just the magnitude of the displacement. Is that satisfying? Okay. All right. Okay. Let's see here. So, yeah, we already know, of course, that x prime is v, and dx is v dt. That's already established, so the rest of that is kind of the same. And let's talk about this TDS point of view, though. This is a nice little argument. I'm making the claim that the dx vector is TDS. So let's start with, wait a second, what is t? So t, oh, whoops, sorry, I wanted to be in the highlighter mode. T, that vector there, is the unit vector that points in the direction of the velocity. It's not the same as the velocity. Velocity has a magnitude that encodes the speed. T is just the unit vector. It's my attempt to have a vector to describe only the direction, right? And only the direction we typically do with unit vectors. So I'm just going to take the velocity and divide by its own magnitude. All right, so why then would it be the case that dx is TDS? Well, I'm going to kind of say, look at the picture. So in this picture here, let me get the colors back a little bit better. Here's our dx vector. I claim it's TDS. Well, dx has a direction and a magnitude. T is the right direction. Right? Unit vector representing the direction that dx points. And check it out. ds, again, I need to be in highlighter mode. ds is the magnitude. Again, previously established. So we don't even really have to do algebra. I mean, you can, by the way. You can take the formula here for t and the formula for ds, and you can just plug them in there, and sure enough, you get the same conclusion. It works just fine algebraically. I like to see it, though, geometrically, as this is the direction of dx. That's the magnitude of dx. Direction and magnitude is what a vector is. All right. So all of this stuff is going to be super important when we get to chapters 6 and 7. That's the main reason I'm spending a bunch of time on establishing all that stuff. So might as well go ahead and memorize these formulas now, because we're going to be using them a little bit here, but we'll be using them a lot later on. Okay, so the little bit here, let's talk about how to compute the length of the entire parametric curve. How do I compute that total length? Right, let's see here, I'll circle the whole. How do I compute that total length? Well, quick argument, I'm going to be looking at a bunch of little pieces of curve, and I want to add that up over the entire curve. I'm just adding up all the little DS's. Right? The whole is the sum of the parts. The parts are ds. Oh, and we have a formula up here for dx. For ds. ds is v dt. And so, boom, we have ourselves a nice, convenient formula for how to compute arc length. If you want to compute the length of the entire curve, you're going to do an integral dt of the speed. Which, by the way, again, I think that makes pretty good sense because you're doing an integral of what you might call ds dt, right? That's what speed is, distance per unit time. So ds dt, dt, satisfying. Alrighty. So the example is very plug and chug. I'm mostly just going to kind of hit the highlights on this. Do make sure that you are good with the details, right? And keep in mind on the exams, you're going to have to do the details as well as the highlights. But class time being limited, we make these tough choices. So we have a parametric curve there. Position is a function of time for certain values of time. And let's see here. We want to compute the length. We have a formula for length. Length is integral of the velocity, integral of the speed, namely the magnitude of the velocity. The velocity, of course, I can get from taking the position and differentiating it. Right, so all I've done in the blue here is take my position formula, take the t derivative, that gives me my velocity formula. So I'm literally taking here the magnitude of the velocity. And then calculation ensues. So you got to compute that magnitude. Magnitudes are square roots. Square roots make for annoying integrands. I'm sorry. This is how these questions tend to work out. The integrals tend to be, I'm going to say super ugly. Very often not even tractable. Just not realistic. The very few cases in which these are tractable are mostly cases where this square root ends up being a constant. So they're either super easy or super hard. It tends to be how it goes down. So anyway. Okay. All right. Okay, so now on to the part that is the little digression that we just kind of need to get said, but isn't really something that we're going to focus on intently. And that mostly is ultimately a plug and chug. Okay, so I'm going to start with an example. I hope you might find this believable. This is a parameterization of that curve. Of course it is. You can literally take the formula for x, and plug it into there, the formula for y, and plug it into there, and the equation works. So it's a parameterization. Aha, yes, but check this out. This is 2. Because you can take the formula for x here. Oh, I missed. Sorry, I went the wrong way. You can take the formula for x, put it there, and the formula for y, and put it there, and it works. So I have here a little eyebrow-raisingly 2 different parameterizations of the same curve. And let me just remind you, that's not that weird. There's lots of different ways to draw a curve. Therefore, there are lots of different parameterizations of a curve. And ultimately, that's what a parameterization of a curve is. It's basically the process of drawing it. Okay, so these 2 different parameterizations, I'm going to say, are easily relatable. I'm going to say that I got it, I could have anyway gotten it, by taking this formula for t and just plugging it in, and that's what you get. Right? So that's really kind of the point here, is that if you can rewrite your parameter in terms of some other variable, plug it into a parameterization, and you get what we call a reparameterization. This is a different parameterization, but of course of the same curve. All right, so it turns out there is a special reparameterization that's very convenient, and that is to use arc length. So if you have position as a function of time, all right, well, you know what else is a function of time? Is distance. Right, and we have an explicit formula for it, in fact, even that S, distance as a function of time. There's my formula. It's just integral of the speed. Right? And so now that you have an algebraic relationship between S and T, okay, solve for T, plug that into there, and you'll end up with position as a function of S. And this is what we call the arc length parameterization. So why do we care about arc length parameterizations? Well, there's a couple of cool things about them. They're intrinsic to the curve. You remember how I talked a lot about how when you're walking along a trail, right? Some people walk on the trail and effectively position as a function of time, parameterize the trail. Some people run on the trail and make a different parameterization because position is a different function of time. They're running faster. Right? So most parameterizations are kind of arbitrary, really. They're more so about the hiker than about the trail itself. This is intrinsic to the curve, namely, I don't really care who it is that's doing the hiking. I'm not parameterizing based on their hiking. I'm parameterizing based on, look, when I get onto this trail, when I get a certain distance away from the trailhead, where am I? It's got nothing to do with time. It's completely unarbitrary, what we call intrinsic to the curve. So that's natural. That's something that's mathematically natural, therefore kind of interesting. Okay. The other thing is it is unit speed, and so if you look at sort of the chain rule applied to this situation and take the magnitude of both sides, and if you think about it, that says magnitude of your velocity, which is your speed. That says distance per unit time, which is your speed. So those two things are the same, and therefore it's unit speed. When you're looking at position as a function of S, when you're looking at the arc length parameterization, that's a unit speed parameterization. That's kind of cool, too. Okay. All right, so again, hard to compute because these integrals tend to be bears, and then even if they aren't, and by the way, I've gone to some trouble here to find a parametric curve where the resulting square root down here, right, the thing we're all afraid of, the thing that makes these integrals stink, right, is the fact that there's going to be this square root. Well, I very cleverly arranged for this to be something where it actually turns into a perfect square. How about that, right? That doesn't happen super often. I'll get right to you. So even having arranged for tremendous good fortune in such a way that I can actually compute this integral, notice I still can't solve for t. Right? So these arc length reparameterizations, they in practice, they're either super easy because the integrals are super easy, or they're intractable. And so in practice, we don't actually do them very much. Yes?
Is that like a cursive capital T?
Oh,
is that
yeah.
Like a notation, like
Yeah.
arbitrary notation, or?
Yeah, that's a great question. So let's go back up to here. I painted myself into a corner. Correction. I was painted into a corner, not of my own doing. Because we have already used T to be the parameter that describes position, so the original parameterization. So T is fixed, and it is for a specific value of T that I want to compute that arc length. And so can I say, well, let's let T go from 0 to T? It doesn't make any sense, right? T is already the endpoint. And if t has to be the endpoint, then it can't also be the parameter. And very common choice in this case is to just make a letter that looks kind of like t, right? Because I'm still thinking of this as kind of being sort of a time of sort, but so we use the lowercase Greek letter tau to kind of get around what would be a mistake of confusion of variables. Yeah. Okay, all right. So this is a good place to draw the line. We will pick up here on Wednesday. See y'all later. Have a good one. Whoops.
Wow.